Hello, everybody. We'll continue this chapter 4, and this section is optimization problems, section 4.7. And I did speak about this, that it's kind of important, and it's similar to the section of when we talked about related rates. So this is the word problems section when it comes to chapter 4. And we need to address a strategy and understand that we're looking, for example, for a maximum, an absolute maximum or an absolute minimum here in this type of problems. So if you look back into like section 4.4, 4.2, a review, you'll see that the extreme value theorem says if f is continuous on a closed interval, then f attains an absolute maximum value f of c and an absolute minimum f of d at some numbers c and d in that ab. And there was that picture like this to present this extreme value theorem. So based on this, if we have a function that is continuous, we're going to look for the absolute maximum or the absolute minimum. And this is used in applications. And the steps, of course, we need to understand the problem. So read it, see what it is asked, what's the question, what is it that's given. If it's something you can draw a diagram, you do it, and you start introducing notation for the variables. But of course, the important part is express Q in terms of some of the other symbols. So we'll express some with others. And you've done this in the past. For example, when you solve a system of equations, you did substitution. So we'll see this in examples. And of course, you solve. So once we do some examples, I would suggest that you go back to review this process so it makes it makes sense and you understand it a little more and what it means to if a Q has been expressed as a function of more than one variable. In step 4, use the given information to find the relationships, and you'll see all those steps. So let's look at a classic, kind of a classical type of problem in optimization. This that shows up sometimes in pre-calc, sometimes in algebra, and now we're going to use it here in this introduction. So a farmer has a 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So in order to get a feeling of what is happening, we do a quick diagram. We have a river, then we have the fence from the three sides. And it could be, you see, it could be different ways. What we know is the total for the fencing is 2,400. So 2,400 can be, let's say, 2,200, 100 this way, 1,000, 700, 700. So you see, there's multiple ways of doing this, and each time the area here is, if you calculate the area, is here about 700,000, 400,000, 220,000. So which one really gives the maximum? That's we don't know. So that's what we're going to investigate. So the way to do that is, of course, it's rectangles. So we have the sides are x, or the width. The length here is called y, and the area is going to be a. And we're going to still think about the length is 2,400, right? And the issue here with having x and y, that's two different variables. So if we introduce x as the width, and we know 2400, that means we don't need to use the y there, because L is going to be x, this, plus x, right, plus y is 2400. So the y is 2400 minus 2x. So that's what's in the strategy to express one in terms of the other. 2400 minus 2x. So then we get into the area. If now x is the width and the length is 2400 minus 2x, then the area becomes the width times the length, right? Which is y. And here, maybe I should use here instead L, say, call it the length of the fence, so it doesn't get mixed up with y, right? And y here is the length of this rectangle, right? So A is x times 2400 minus 2x. So let's look at it here. You have A is xy, and here this is not shown, but it show it that if you have an x here, then this must be x, and what's left here is 2400 minus 2x, right? So that's what I showed, and you multiply. So we get to this step here. We say A is 2400 times x minus 2x squared. So the area is represented by kind of a parabola. And we know for parabolas, if A is negative, it looks down and it has a max. So that's good news, means there is a maximum here for an area, it can be achieved. And we've done in algebra how to solve it, and now we're gonna, or in pre-calc as well, and now we're gonna use the calc method. The calc method, of course, is you're going to take the derivative, and for the 2400x minus 2x squared, it's gonna become 2400 minus 4x, and we're going to set it to 0 because we need to find the critical value, which is the 600. So that's a critical value. And now for this interval in which we're working, right? The 0 to 1200, the maximum value of A must occur either at the critical number or at an endpoint. So how can we know that? Is if we use these values into the function and substitute them like the y value, so see which y is higher. So let's recognize, of course, this part here of where this 1200 came from, right? Because it's from this note here that the largest x, it can be 1200. Because if you have one x, one width, you have to have the other width, that's 2x. The whole thing is 2400. If you divide 2400 by 2, that's 1200. So that's the highest possible thing for x, right? So think about it that way, x and x. And the whole thing is 2400. So if we divide it by 2, that's the maximum that x can be. But of course, it's not going to reach 1200 because then you won't have the y and you won't have rectangle. But just to show where this come from. So if you know these ends, this is the lowest, and this is or the minimum, and this is the highest or the maximum, right, for X. Then let's figure out what is A of 0 and what is A of 1200. And now we have a point, a critical point 600. What is A of 600? So A of 0 is 0. A of 600 is 720,000. A of 1200 is 0. So the closed interval method gives the maximum value at 600, which is 720,000. So of course this is the absolute max from what we can see, right? Alternatively, we could observe, we could also do the second derivative test. And if you do the second derivative test, you'll find out that it's -4. And that means it concaves down. And of course, there is a max there. And the local maximum at X equals 600. And of course, whichever test you do, you're going to find that the maximum happens there. So the corresponding Y value is 2400 minus 2 times 600 is 1200. So rectangular field should be 600 deep and 1200 wide. So this is, here we found the Y value. So let's show another thing here based on this. A note in algebra, in pre-calc, how this is solved is to do the vertex. You do x is negative b over 2a, right? 2400x minus 2x squared. 2400x minus 2x squared. So, which is negative 2x squared plus 2400x, right? So negative b is negative 2400 over 2 times negative 2, which is 600, right? And you remember for the vertex, when you find the first one, you substitute this into the function to find the maximum value. And that's or the maximum area, 2400 minus and we need it here because that's the area. So we need this 600 here minus 2 times 600 squared, which was done here as 720,000. So this is the maximum area, and which so here that's a as the function f. And we did at the beginning, y is that 2400 minus 2x, which is 1200, right? And to the 600 here to 2400. So now you can see the pre-calc way method is this, but the calculus method is we'll set up same way. By figuring out this interval, and when we do a of 0 and a of 1200, we find out this part here, the 0 and 0. Then when you do 600, you find the absolute maximum. So there is a maximum at 600. And that's it. So what is the Y value there? We go back to that and replace it. So the maximum area is going to be happening at 600 at 1200. So remember the part here where we did the switch, right? Of 2x plus y is 2400. So y is 2400 minus 2x, then we put this into this formula. So that's how these work in a way. Of course, each problem is going to be different, but overall, that's how the steps work. So the first derivative test for absolute extreme values again. Suppose that c is a critical number. Then for a continuous function, if f prime of x is positive for all x less than c, then f prime and f prime is less than 0 for all x, then f of c is the absolute maximum. If the f prime is less than 0 for all x less than c, and f prime is positive for all x greater than c, then f of c is the absolute minimum value. So this is just like what we talked about previously, right? So A, if f prime of x is positive for all x less than c, so this is so all the x's less than c, we have this case, and f prime of x is less than 0 for all x greater than c, which is this side. And of course here the word is all. So when we say all, then it means now we don't just say we have a local maximum, but we have an absolute max there. And same picture for the C and for the B case, right? Then you say you have an absolute minimum, because here it's going to be the other way, right? All right, let's look at an example from a lecture activity, and there is one problem there. Consider, and this will help you kind of start understanding this optimization problem, why this technique is useful, because it could be hectic investigating, and this is a simple check. Consider the following problem. Find two numbers whose sum is 23 and whose product is a maximum. So if you take one, you need 22 to get a sum, 23. All right. And if you take two, then you need 21 to get to sum 23. So the numbers add up to 23, but their product is a maximum. When you do 1 times 22, you get 22. 1 times 21, you get 42. 3 times 20. So I completed with these numbers, and we keep going. So these green ones are the ones you need to fill in. So if you have a 4, then you need 19, right, to get 23. Then you do 4 times 19, you get 76. So as you see here, as these numbers increase, of course, because 23 is constant, these numbers start to decrease until you reach the point of 11. When you reach point of 11, 11 plus 12, you get 23. And when you multiply them, you get 132. So the next one is 12. And you need 11 to get 23. So it repeats. 11, 12, so it's the same combination, 11, 12, 12, 11. So that's where we're going to stop, right? Because after this, we're just going to repeat, right? If you do 13, that's a 10. So that's why you stop at 11. And 11, you need 12 to get 23. 11 times 12 is 132. So this 132 looks to be the max. in this case, right? So find two numbers whose sum is 23 and whose product. Complete the table so that the sum and this and that. On the basis of the evidence of the table, answer the problem, and we can say now 11, 12, right? So that's it. On the basis of the evidence in the table, we estimate the answer to the problem. So estimate. So the word here is the estimation, right? So keep in mind this. Now let's use calculus to solve the problem. So we'll follow the same method. So let x and y be these two numbers, and their sum is 23, and their product is going to be some type of a maximum, right? So let's say that. So from here, so we can say that this will allow us to have y to be 23 minus x. So we can use it here, and we can get now this 23x minus x squared, just like the area for that example. So we can do a first derivative to find that 23 minus 2x, and set it to 0 will give us x to be 23 divided by 2. This numbers we started, if we investigate a little more, if we want to look at the second derivative, it's going to be -2, which is negative. So yeah, so it concaves down. So there is that max, and that max is this 11.5. And if it's 11.5, the y, which is 23 minus x, it's going to be 23 minus 11.5, which is 11.5. So that's so you can see when we did the note, when we did the estimate, we found 11, 12, and when we did the calculation, we found 11.5, 11.5. Now, what is the maximum? And this is now from the homework point 7, number 3. What is the maximum vertical distance between the line y plus 2 and the parabola y equal x squared? So I put this graph here to show, you know, it's hard sometimes to see what we're looking for if we don't have this graph. So y equal x plus 2 is this, and the parabola is this. And the question is, what is the maximum vertical distance? And you see this vertical distance, it becomes 0, then it changes. So what is the maximum vertical distance here between these two? So one thing to do, maybe we can call it V. It means that we need to do a difference between a vertical distance. So if this is the y of this line and this is the y of this graph, then let's say y2 minus y1 is going to be that distance, right? So x plus 2 minus the x squared is going to be that difference there, which is x plus 2 minus x squared, so the function. we take its derivative, and it'll be 1 minus 2x, and we set it to 0, gives us x is 1/2. So now let's check, investigate. We have -1 x2. If you do v to -1, we get 1 minus 2 times -1. We get this is v of -1, which is this. So -1 plus 2 minus -1 squared, -1 plus 2 minus 1, and -1 plus 2 is 1, minus 1 is 0. Then we need to do v of 2. It will be 2 plus 2 minus 2 squared. So that's a 4 minus 4, that's a 0. Now let's do v of 1/2. So it'd be 1/2 plus 2 minus 1/4. All right, and that's gonna be, we make all 4, so it's gonna be 2/4 and 8/4 minus 1/4. So that's 9/4. So as you see in this interval, we expect to have a maximum, this interval here. These are zeros, these y values are zeros, and this v of 1/2 is 9/4, which means that's the absolute max, right? So this is the absolute maximum. And if you want to investigate, you can also use the second derivative. And second derivative is -2, which is concave down. So that also says that we have absolute maximum there. So we know now there is an absolute maximum at the critical point, this critical point 1/2. So we just need to figure out what is that maximum distance. The maximum distance is just going to follow that formula, which is v of 1/2, which we did. Let's just show it again. If I want to show it as 1/2 plus 2 minus 1/2 squared, which is 9/4. So that's the answer. For this number 5, we have a rate, and for which photosynthesis and takes a place, and right. For species of phytoplankton is modeled with this function, and where I is the light of intensity measured in thousands of foot candles. For what light intensity is P is a max. There is a maximum there. And this question, so for what, for what I, there is the max, right? So we'll start with the, as usual, again, as a derivative. So let's take the derivative, which means we need to do the quotient rule here. Of course, with respect to, so p prime of I, means here dp di, so the derivative with respect to I. Let's factor 110. And let's simplify. And we get, yeah, so we have a negative common, so you have I squared minus 2I squared, that's negative I squared. And I cancels with this one here. And you have plus 1, so you have 110 negative I squared plus 1, right? And you have I squared plus I plus 1 squared. So when you take a negative out, you'll have I squared minus 1 because that's a better form, like a difference of squares, which can easily factor to I plus 1 and I minus 1. So there are two numbers there that we need to investigate from there. So when we say the first derivative here equals 0, of course the fraction means the numerator is 0, which means this I plus 1, I minus 1, this is not 0, means I equal negative 1 and 1, right? But of course the intensity is going to start from 0. Since the intensity is positive, we need to investigate here. You can do the full analysis if you want for as you do for functions, but here really we're interested and let's investigate this number, because if you put 0 here, negative 1 is on this side, and you have 1 on here, right? So we need to find out what is this a max or not? If this is a max here, then the first derivative has to change sign on the left side and right side of 1, which means we have to have a max. And a max means here the first derivative is positive and here is negative. And of course, f prime of 1 is 0, which is, we know now it is. So let's just check that. So take 0.5, a number, and try it, and you're gonna find that's the case that's happening. So if you check 0 to 1, you're going to find f prime, which is in this case p prime, to be positive. And if you check or test on the right side of 1, let's just say 1 to infinity, you're going to find p prime less than 0. Try it. So you have the formula. Here is the formula of the whole thing. Even try the whole thing, right? And that's what you're going to find. And since it changes from positive to negative, it is p prime, it is 0 at 1. We can say that there is the max, the point we're looking for, the absolute maximum is at I equal 1. So that's the answer. And if you are interested, you're going to substitute 1 into I, and you're going to find 30. Let's look into another type of problem where we have a box of material and it's available. It's let's see a few things here. It's a square box. It's open top. Find the largest possible volume for this box. So it's a same idea again. It just now we need to think about it that way. Let's see, maybe do some sketch here and something like this. So you can see that if you have, you know, the bottom of the box, which is, if this is B, then the area, the base, if we call it the base here, is B squared, and this is H, the height. All right. So let B the length of the base, and let H to be the height. So the surface here is going to be because the material available, that's the surface area, that's the total surface area that we're going to use. So the surface is 10,800 centimeters square, and where this is going to come from is going to come from the base, which is B squared, right? And you have these sides, which is B times H around, right? All around. So that's 4 of them. And no plus top because of this, it's an open top. So usually you have 6, right? So, but here we have 1, the base, and we have 4 sides. We're supposed to have the top, but it's not there because it's an open top. So that's how this material is going to be used. And from here, it looks like we can get H out. So solve for H as 10,800 minus B squared over 4B. And the volume formula, just like we did for the other example for the area, here is going to be the base times the height. Base is B squared and the height is H, so it's going to be B squared times this thing here. So there is always a substitution process that happens, and let's a little bit simplify it. It's going to be B squared times 10,800 divided by 4B. That's going to be 2,700B. Then we have B squared times B squared, that's B to the 4th power divided by 4B. Is going to be B cubed over 4. Once we have the formula, then we move on. Now take the derivative, which is in terms of B, of course, it's given. And it is 2,700 minus 3/4 B squared. Then we're interested in this first derivative to be 0. So we will solve it. 2700 equal 3/4 b square. So b square is 3600, and b is going to be 60, a square root of 3600. So here we'll do the same thing. We're going to investigate this maximum thing is between a 0 and a 60, and what happens for v prime. All right, so we do the same, do the same work. B is going to be between that 0 and 60. Let's just do 0 and 60. And be greater than 60, or this is a 60. Of course, the base cannot be below 0, so that's why we stop at this 0 here, and we investigate. So take any check from here, let's say 50, and any check from here, let's say 70, and let's try it into this function of v prime, right? So let's try it on the side, maybe try a 50 or a 40 or a 10, anything between 0 and 60, and see what happens, right? So I'm going to try a number here. And it comes up to be a positive here. And if you try a number here, it comes up to be negative. And that tells us there is a maximum. Since the first derivative here is a positive, means it's going up, the function, and it's coming down here when it is negative. And since it's 0 there, that means there is a maximum there. So there is a maximum at 60, right? And we already talked about B formula. Let's show when we started, and we have H. So now that we know B is 60, and we need H, we can go back to that formula for H. So H is 10,800 minus 60 squared over 4 times 60, and that equals to 30. So the maximum volume that this surface area can cover is B square H. So we will use a 60 square and a 30, which will give us 108,000 centimeter cube. All right. So it's not bad. Just keeping the same idea of finding the first derivative, investigating that critical point, whether it's actually that maximum or minimum you're looking for, and going back to substitute, because you use that substitution in order to solve. So you go back to, like we did back to H here to find it. Then, of course, we can answer the request. For this last problem here, find the point and the line. This is actually has a nice trick that may not be shown in the book or somewhere. So let's talk about this as a last example. Find the point and the line that is closest to the origin. The origin is 0, 0. And let's say 1, 2, 3, 4, this point here, and you know, you do up 4 and this, let's say you do the slope and you graph. Something like this. And so the distance between this this origin and this line, it could be something like this. So maybe this is the point we're looking for, and you know, x and y, and any point on this line, of course, any point on the line is x, and the y is 5x plus 4. So that's what we're looking for here. The distance between these 2 points, and we can also rename it. So any point, just keep this one, x and 5x plus 4. So any point in that line is x, and its y value is 5x 4, and the 0, 0. So the distance between these 2 points, if we use the distance formula from algebra, it's going to be x minus 0 squared plus 5x plus 4 minus 0 squared, which is x squared plus 5x plus 4 squared. One trick, a nice trick to use here is based on a logic that if the closest or the lowest, if the lowest number you're looking for, then its square is also going to be a lowest number. So a logic that if d is lowest, right, then its square is also lowest among all the squares, right? So this is to make this problem easier to do. That's what this trick will do. So instead dealing with the square root and all this, we're going to remove a square root, and we're going to say s is a d square, which is x squared plus 5x plus 4. And s now it's like that distance, but it's square, because that square is also going to be the lowest among all the other squares of all the other distances. So now if we take the derivative, you see it's we don't have to deal with the square and all that. It's 2x plus 2 times 5x plus 4 times 5 with the chain rule, and it's we have a 10x, a 50, so a 52x, and a 40. And we do again, we set it to 0. So x is 10 over 13 when you simplify. All right. If you want to do the other way, if you want to investigate using the second derivative, you know, it's 52, and it's also going to be positive, right? It's greater than 0, which means it's concave up. So concave upward, which means there is a minimum there, right? So minimum at x equal negative 10 over 3. And because of that, now the point is negative 10 over 13, and we need the y, and we get the y from using this equation. Right. So it would be 5 times negative 10 over 13 plus 4, which will give us 2 over 13. Okay, thank you.